For the second part of Chapter 9, Natural Causes of Climate Change, we'll look at much longer-term natural phenomena that have timescales of 10,000 years or more. We'll look at orbital variations in Earth-Sun relationships. We'll look at the distribution of continents and how plate tectonics has modified ocean heat transport and also the piling up of snow and glaciation on those continents. We'll look at variations in sea levels and in the ocean transport processes as well. And finally, an extraterrestrial impact. The first cycle is eccentricity, the tendency for our orbit around the sun to go from more elliptic to more circular and back to more elliptic over a period of 100,000 years. This changes the amount of sunlight hitting each hemisphere during the seasons, and also there's slight changes in the length of each season itself. Second cycle is obliquity, or the tilt of Earth, which we go to a state of being more tilted, 24.5 degrees or so, back to a state of being less tilted, 22.5, and then back to 24.5 over a period of 41,000 years. This certainly changes the summer to winter difference in temperatures and solar radiation. Lastly, the precession, or the wobble of the Earth. Earth wobbles about its axis over time of a period of 21,000 years. What this does is changes the distance from the sun during the seasons. Right now, Northern Hemisphere summer, we're at aphelion, which is the farthest point of the orbit from the sun. But Northern Hemisphere summer will be at perihelion in about half that cycle, or 11,000 years. Just another graph looking at the aphelion, farthest point from the sun during our orbit, and the perihelion, the part of the orbit with minimum Earth to sun distance. Currently, Northern Hemisphere winters at perihelion when we're closest to sun, and that gives us a more mild winter, and Southern Hemisphere winters at aphelion, giving them a more extreme winter. With Northern Hemisphere winter currently at perihelion, which hemisphere has the largest seasonal contrast in solar radiation? And that would be the Southern Hemisphere, since they're far from the sun during winter with low solar expected, and close during summer, higher solar. However, the actual temperature difference between the hemispheres may not be that pronounced because the Southern Hemisphere has a much larger percentage of ocean, which moderates temperature. The difference in seasonal contrast between hemispheres larger, the larger the eccentricity is. In other words, if the orbit was perfectly circular, then the Earth-Sun distance is the same at perihelion and aphelion. So there would be no difference in the solar radiation range between the hemispheres in that case. However, you could suspect that the Southern Hemisphere with more oceans would have a more damped temperature change over the season than the Northern Hemisphere. This animation is showing that the time spent near the sun is shorter during perihelion, and that's because as you get closer to the attractor in these orbits, you move quicker. So right now, Northern Hemisphere winter is milder and a bit shorter too compared to Southern Hemisphere's winter. It turns out, however, that the timing here is not as important as the actual Earth to sun distance. Obliquity, the tilt of the Earth, influences the difference between the summer and winter solar fluxes. Right now, we're at 23.5 degrees off vertical, but again, it varies between about 22 and 24.5 degrees. With more tilt, you'd expect more seasonal contrast for both hemispheres. That means the solar flux would be coming in more perpendicular than typical during the summer because you're facing the sun more directly. And as you rotate around to your winter time, that means the sun's coming in also at a more extreme angle, giving you less solar radiation during your winter. So again, more tilt means more seasonal contrast for both hemispheres. Now the precession feeds into the eccentricity as well. Just like a teetering top, the orientation of our tilted planet changes with respect to the elliptical plane. Here the spinning top kind of shows it pretty well. As we're rotating around the sun, we're also wobbling with a period, again, of about 26,000 years. Overall, this precessional cycle is really caused by the moon and the sun pulling on the bulge at the equator. So the Earth is not a perfect sphere, it's a little bit chubby at the equator, and this gets pulled preferentially by the moon and sun, helping to lead this precessional cycle. So perihelion switches between Northern Hemisphere summer and winter every about 11 to 13,000 years. This is a result of that wobbly nature of the Earth, and this is a result of the precessional cycle. The way you could detect this would be looking at the change in the star's position over time, looking along the axis. In other words, looking to the north. We're looking towards the North Star if you look directly north. However, in about 13,000 years from now, we'll be looking at the star Vega, which is an indication that we are wobbling over time. Now we can look at how all these cycles are interrelated and how they impact glaciations. First of all, Because most of the world's land is combined in the northern hemisphere, we tend to look at the northern hemisphere because that's where you get a piling up of snow that might stay throughout the summer if it remains cold enough. So we tend to look at 65 degrees north in the northern hemisphere when we're looking at solar radiation differences caused by these orbital cycles as an indication of if we're preferred for overall glaciation or if we're not. So northern hemisphere glaciation is promoted by a precessional state such as today with our northern hemisphere summer at aphelion when we're farthest from the sun. That will give you a slightly long yet not so hot summer because of the distance is maximized during our summer. The northern hemisphere glaciation is especially favored when the eccentricity is large and northern hemisphere summer is at aphelion. This will give you the maximum distance between the Earth and Sun during that time and during that summer, which will give you a long, yet really not that hot summer. Again, allowing whatever snow piled up the previous winter to perhaps persist throughout the summer so you can pile up more snow the following winter, leading to a glaciation over long timescales. Having low obliquity would also help keep the summer less hot because in general, that simply means that you're not tilted towards the sun as directly during your summertime. This graph looks at all those orbital cycles. The top graph here is looking at the impact, the insolation at 65 north due to a combination of those cycles again. And what we're looking at here, which we'll get into in later lectures, is the deuterium content, or the isotopes that are accumulated in the snowpack in Antarctica. And so it turns out that's a pretty good gauge on atmospheric temperature through some complex processes that we'll look at. For now, I'm just going to let these balls roll here and see that there is a pretty good relationship between that solar insolation at 65 north and your temperature overall. So insolation changes are linked to these orbital cycles. The combined effects at 65 north matches glaciation cycles in the last 700,000 years or so. However, it turns out that those insolation changes are actually really small. They provide a perturbation to push the climate towards one direction of cold or hot. However, you need a lot of positive feedbacks in the system to amplify those initial effects. So the insolation changes themselves are not enough to push the climate between glacial and interglacial times. You need to have some internal feedbacks in the system, and there's plenty of them that we'll look at in this class over time. So the distribution of continents. First of all, plate tectonics we're going to have to describe here with a short video to see how continents are actually pushed around the globe over time. So let's take a look at that first.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So where this primarily happens is at the mid-oceanic ridges, where areas where mantle is coming to the surface, helping push plates apart, which ultimately puts all the continental plates and the oceanic plates into motion. So this is the process by which plate tectonics moves plates around. Having continents near the poles can lead to cool periods. This is because the oceans are not able to transport heat and move it to the pole in that case. They're blocked by the continents from doing so. As we've seen, the thermohaline circulation does a good job these days of moving warm surface currents towards the poles, where ultimately they sink and help drive the thermohaline circulation, but in the process they're actually heating the poles through that. If you put a continent there, that can't happen. Continents can also accumulate snow if they're at the extreme poles, which can raise the overall albedo of the Earth as well. Having continents along the equator, however, has led in the deep past to what are called several snowball Earth episodes. How this happens is there's a process by which the weathering of a rock, inorganic rock that we'll look at in the carbon cycle, by rain can actually draw down atmospheric CO2 on millions of years timescales. So if you position them at the ITCZ, the very warm part of the world where there's a lot of rain, you get rain on rock, and eventually you'll draw down CO2 quite a bit over extremely long timescales. What happens next? The poles will freeze first. The poles will tend to get the worst effects of that cooling process if you're drawing down CO2, but weathering can continue in the tropical zone because it's still warm enough to support rainfall and not freezing the continents that exist there. Once the actual Earth freezes to about 30 degrees north and south, starting from the poles downward, you actually get what's called a runaway albedo effect, meaning that the reflectivity is so high over the planet that the rest of the planet will freeze over as a result of this positive feedback going towards cooling. So let's look at a little animation of how this works with the two cases. In the first case, if you have land near the poles, they simply can gather snow and ice, giving ice caps. Can also block oceanic heat transport. But the weathering of rock will shut off when it freezes, so there won't be a large-scale weathering event which draws down CO2. It will just give you an anomalous cold event for some time. If you really want to freeze the entire planet, it does help to have land at the equator so that that weathering can continue drawing down CO2 for such a long time until the ice can actually get down to 30 degrees north or south. Then that ice albedo feedback will take over and freeze the entire planet. This has only happened possibly 2 or 3 times in the history of the Earth, but it is something worth mentioning. Since plate tectonics push these continents around, that can actually change the volume of the ocean basins and can drop or raise the sea level as a result of simply changing the volumes available to capture seawater. It can also change the ocean currents as well. You can deflect the ocean currents if you move a continent in their path. You can also build mountains by having continental plates push into each other. Those mountains can therefore form ice, raising the albedo on average of the planet. Mountains can be weathered too, dropping CO2. For example, when the Himalayas rose, there was a pronounced drop in CO2 over long timescales because you had mountains in a place with a lot of weather, and a lot of weathering drew down CO2. You can also push oceanic plates into subduction zones, which that video showed can cook CO2-rich rock and eject it through volcanoes back to the atmosphere. That can raise CO2 over very, very long timescales as well. Looking here at variation in the oceans, so anytime you change the sea level, that's going to change the relative heights of the continents and the areas of land versus ocean as well. That will change the overall global albedo, since land has a higher albedo than the ocean, and it will change the amount of weathering available. More continents and places where there's weather, again, can draw down CO2 on very long timescales. Oceans have very large heat storage, and this can change based on a number of things, including the depth of solar penetration, so what color is the water, how much stuff's in the water to prevent it from mixing down deeper, and also ocean dynamics. How do waves and winds actually help promote and mix heat down to the deep ocean, where it might sequester it for longer periods of time. The oceans currently perform around 50% of poleward heat transport. We've looked at these numbers, and this can change due to the continental positions and thermohaline processes. So anytime you change where the continents are, you change those currents, you change how efficient they are at transporting heat poleward. The Younger Dryas is a good example of the thermohaline process and how it can really change climate. What this was an event around 11,000 years ago. So 20,000 years ago, we were coming out of a great ice age, which was a time where there's extensive polar ice caps. As we began to emerge from that, and it's really tied with the Milankovitch cycles, that emergence of that, all of a sudden we went into this really cold snap period called that Younger Dryas period. How we know it happened was this Dryas flower, which is an alpine flower, typically found in the high alpine, was actually found in lower elevations, especially around Europe. So we can look at the fossil record and find evidence of this. So the question is, well, what happened? Why did we all of a sudden abruptly return to colder conditions when Milankovitch cycles would have said that we should have been warming? So what happened exactly? Well, the thermohaline circulation appeared to slow down at this point. And what we think the reason was there's a sudden inflow of fresh water into the North Atlantic, most likely due to a sudden drainage of a large glacial lake over here in the St. Lawrence River, coming out into the region where typically you're forming your bottom waters. So if you dump a bunch of fresh water, which is less dense than salty water, that prevents the water from sinking, and that shuts down or slows down the thermohaline circulation. As a result, that backs up the surface current that feeds that sinking water, and as a result, you're not pushing as much warm surface water towards the North Atlantic as usual. And this makes sense because Europe is the place that was most affected during the Younger Dryas, and they're also the place these days that get the most impact, the most warming from that surface current coming up the North Atlantic, since the winds will blow west to east, blowing that warm anomaly towards their climates. Finally, looking at extraterrestrial impacts, more specifically, we look at an asteroid impact that occurred around 65 million years ago. What appeared to have happened was that it scorched vegetation. This removed oxygen from the system because you took down vegetation, which is the primary contributor of oxygen, and it added CO2 from the decay of those plants over a period of months and years, halted photosynthesis in general, loaded the atmosphere also with dust and smoke since the extreme impact caused fires, and this led to cooling. Chemistry effects were also in there, and there's a bunch of elaborate studies about this, but ultimately the ozone layer was thought to be harmed. After months of cooling, the temperatures actually rebounded higher than before, and this is because we had more CO2 in the atmosphere, greenhouse gas, and less stratospheric ozone, allowing more high-intense sunlight to reach the surface. The animals could not adapt well during this, and this is the time where we see the extinction of the dinosaurs, and it's likely related to this quick climate shift. The KT boundary event increased the seasonal temperature range for the northern hemisphere for millions of years. How exactly would that happen? Well, the impact wasn't large enough to change the eccentricity, so that's not true. The impact did not shift the moose position. However, what it did was you had less plants. Less plants led to less wintertime CO2, and less plants would lead to more summertime CO2. So let me explain that. In today's Earth system, when you have the summertime, you actually get a lot more plant growth, and that drives down CO2 because they use it for photosynthesis. So that keeps the CO2 lower in the summer than it would be without plants. During the winter, what happens with plants around is they start to decay. That releases CO2 from decomposition processes. So we end up today with more CO2 during the winter, which helps trap heat and keep our winters a little more mild. Back then, without plants, again, you'd have less plants, leading to less winter CO2 and leading to more summer CO2 than today's climate. And that itself would increase the seasonal temperature range when you did not have plants. Key points from this lecture: Earth-Sun relationships paced glaciations over the last 2 million years. But these are long timescale processes. These Milankovitch cycles are not influencing the modern record of temperature that we're seeing in the last 100 years or so. The distribution of continents has an effect over long timescales. Land at the poles can cause cooling because you're piling up snow, you're limiting the oceans from transporting heat poleward, and if you push a lot of continents into the equator, you can force snowball Earth at least a couple times, 2 or 3 times over the course of history. Variations in the ocean, such as circulation and heat storage, obviously change climate. And finally, the real lesson from the extraterrestrial impact we looked at 65 million years ago at least shows that quick climate change can help drive extinctions.